So I would like to introduce everyone to our speaker this afternoon, Kristen Hammer. She is the Materials Engineering Manager at Hyperloop One in Los Angeles. So I met Kristen when I was on a consular visit to Los Angeles in January of 2018, and went on a tour through the Hyperloop facility. Very interesting. Thank you, Kristen, for that. And thought, well, what a great idea to have her come up here and speak to all of us regarding Hyperloop and where it's going into the future. So she leads the Hyperloop One's Materials Engineering program, and she was one of the first employees for Hyperloop One back in 2015, so she's been there for a few years. She's also led the welding and inspection efforts at their DevLoop facility, which is their test facility for the Hyperloop. She graduated with a degree in welding engineering. Welding engineering, and I didn't even know there was such a thing. Welding engineering from Ohio State, and has worked at Westinghouse Nuclear, Honda Research and Development, SpaceX, and several other aerospace companies. Spent some time as a welding engineer working on a variety of welding technologies: electron beam welding, TIG welding, MIG welding, stick welding, flux core welding, and a variety of other types of welding. Johan, you might want to connect with her since you like welding. Kristen's a native of Delaware, Ohio, just north of Columbus, and has been a member of the American Welding Society since 2009. I'll also introduce her partner, Matt. Stick your hand up, Matt. Matt, who graduated with his bachelor's and master's in mechanical engineering from MIT, and now himself works at SpaceX. So we obviously have a power couple here. And Kristen's going to be talking to us today about the impact that her mentors and faculty, people just like yourselves, have had on her career trajectory. Kristen Hammer.
Scooch this over a little bit. Can everybody hear me okay? Okay. If I'm too quiet, shout, especially in the back. Shout out to Carrie for giving me a matching lei with my shirt, because I feel very festive now. I did not have a Hawaiian shirt in my repertoire, so I went for festive colors and flowery shoes, so I'm kind of participating. So thank you for the introduction, Forrest. I think everything is pretty much covered there about me, so I'll dive right in. I've got some good slides here to present to you guys kind of what the Hyperloop is for those of you who don't know, and then I'll kind of talk about how I got here and talking about the people that helped me get here, because it certainly wasn't all on my own. So we're really trying to create a new technology that transforms the way that we travel around the world. So I'll go through kind of the technology itself, but first I want to talk a little bit about the impact. So the Hyperloop is a system that's designed to connect cities to one another. So this isn't a system for within a city, but rather connecting large cities to each other. And we think this is pretty cool because it can turn these metro cities into kind of one large accessible area. So this is a really unique example for me. This is an actual route that we're working on. The Mid-Ohio Regional Planning Commission in Columbus, Ohio proposed this route to us as part of an initiative we had a few years ago to kind of build knowledge on the Hyperloop system. And basically it goes from Pennsylvania and Pittsburgh to Columbus, Ohio to Chicago. Now, Chicago is the big city that everybody's familiar with, lots of jobs, expensive housing. Columbus and Pittsburgh are these kind of middle-sized cities, lots of tech and lots of jobs happening there, much cheaper housing. So if you can access Chicago from Columbus and Pittsburgh in 20 minutes or 45 minutes, then you could feasibly commute from Pittsburgh or Columbus to Chicago every day. So you don't have to pay the prices to live in Chicago, but you can have the accessibility to work in Chicago. That's really what we're looking at here, is connecting cities at a price that is cheaper than flight and at a cost and at a speed that is faster than flight. So it's kind of this crazy new thing that really changes the way that cities work together and that we think of city areas. So cheesy marketing line, but turning metros into metro stops. We'll get through some of the details of the tech right after this, but keep in the back of your mind, so this kind of, we're connecting cities in a much simpler way. And there's a lot of opportunities for how this affects those cities. So think of how this can fit into a smart cities concept. Think of how this could fit into a smart grid concept as we go through the tech here a little bit. So what the heck is this thing? We have a pod. Biggest difference from this being like a high-speed maglev train or a high-speed rail system is these pods as individual pieces. So there's 25 to 35 people in these pods, and they're all individually kind of packaged. So if we're thinking of a route that goes up and down the West Coast here and connects down to Seattle and Portland and San Francisco and LA, if I'm coming here from LA, but somebody else is going LA to San Francisco, we're not on the same pod. So we're going to our individual pod at the station that we call portals and getting on our pod and going straight to the city that we're going to. So you're not stopping at cities in between, which really saves a lot of time. So our system is faster than high-speed rail and maglev, but it's also this kind of direct-to-destination, on-demand aspect of traveling that's really unique compared to other train-based systems. So this pod is inside of a tube where we pulled out most of the air, reduces the air resistance to a point where we can get a huge aerodynamic advantage, but we're not at a space level vacuum. That's really hard to maintain, really expensive. So we go to this just kind of sweet spot in the middle. The pod is levitated with magnetic levitation and propelled with a linear electric motor. So think of a standard motor kind of unrolled down the length of the tube. You can kind of see, I don't know if my mouse shows up, you can kind of see down at the 6 o'clock position on the tube, these white segments. Those are the motor segments. This is an exact replica of our DevLoop test route. And then on the side, the shiny aluminum looking pieces, as I point to my screen that nobody can see, those are the levitation rails. So in the case of DevLoop, we send current through those white coils, those motor coils. That creates a magnetic field, which interacts with magnets or electromagnets on the pod. And then as the pod picks up speed, magnets or electromagnets on the arms of the pod kind of interact with these levitation rails and give us levitation. So we have no wear or friction from wheels. We have little friction from air. We can go really fast. The whole thing is autonomously controlled. So no operator in your pod, just passengers going where they're going. And this autonomous control allows you to, hypothetically sit here, get on your phone on the app, call your Hyperloop journey. It directs you to the portal here in Vancouver, directs you to your pod that's going to where you're going. You get on your pod, everybody else hops on. You're not scheduling this ride hours, days in advance. You're deciding you want to go somewhere now. You're going to the station and you're going. So it's really just fundamentally different from what else we have out. It's inherently safe. So if you think about the ways that other transportation systems fail, we really don't have a lot of those issues. So we're inside of this tube. We don't have to worry about weather. We don't have to worry about people leaping out in front of us. A lot of the issues that autonomous vehicle technology is facing right now just don't exist in our system. If somebody were in the tube, they'd have to be in a spacesuit anyways. So that would be a problem, but there's not a way for a person to get into that environment in the first place. So it takes away a lot of those issues. We've developed a high-speed switching technology that's really cool. One of the biggest technical challenges, had you asked me a couple of years ago, was this high-speed switching thing. And we came up with a couple of solutions and have narrowed down to this really nice, safe system. Know where it's, like I said, take away a lot of these issues that other systems have for safety, and it's really a pretty safe system. The whole thing is electric as well. So no direct emissions. We're not sending pollution into the air like combustion engines or diesel engines. This picture here is kind of cool. You guys can see that we've got the Hyperloop set down the median of a highway. So completely possible for us to do that. We like long, straight routes, highways, rail lines, old rail lines. These are some really good candidates for where a Hyperloop can be built. And this also has solar panels on top. There's not really anything else we're doing with that space on top, so there's no reason why we couldn't build solar panels on top of the tube. So this is kind of where we get into that. How could some system like this interact with the grid to maybe help regulate the energy in the entire grid? So sometimes we're pulling, sometimes we're pushing energy. And it opens some unique possibilities in a lot of regions. I've got a little bit of a video here that I want to show you guys. We call this the Building DevLoop video. So it's got a lot going on. We might watch it a couple times. Let's dive in here. This is DevLoop in Nevada, so 500 meters long, 3.3 meters in diameter.
Was seeing just
no room to build this in downtown LA, so that's why we went to Nevada.
Completely bare, and you saw in your head, in your mind's eye, what we were going to put there.
This is our CTO and co-founder talking in the background here.
I have a tremendous confidence in the people that
That's the headquarters
I
in
work
LA.
with, and the people on the team that I helped build.
You've got teams from mechanical design.
Headquarters again when Richard Branson came to meet all of us.
People who've worked on massive
This is the
motor
pod frame that you're
systems,
seeing.
rocket
So it
ships,
looks a lot like a race car
aerospace,
frame.
Aerodynamic engineering.
This thing that started as a sketch and an idea.
It's the pod frame
and then
again.
live on this computer
And this is the
now
aerodynamic shell
real,
that goes on top of the
and
pod.
it's
So you'll
welded
see
and
another
it's
shot of that
bolted,
coming
and
up.
you put your hands on it. And then we actually assemble all the parts onto it and set it up to site.
This is
And you
inside the
flip
tube
power
with
switch and
the
it just
cool
comes to
lights.
life. That's really the engineering dream, to get to see.
And that's the
that
sled
whole
itself,
process
so just
through.
the frame during initial testing. And this is with the aerodynamic shell atop the frame.
To think we did all this in 10
Testing inside
months.
the tube.
We proved to the whole world that we can build safely, quickly, efficiently, and prove the technology works. This is
Engineering
just the
excitement
beginning.
as we went through our
This
first couple of
company,
tests.
like others in the Virgin family, has insatiable curiosity and the grit to get it done.
I can't wait to see what we do next as a team.
So a lot going on in that video, really hard for me to narrate, and then you can't hear what the people are saying on the video. So I'm going to just go through it again and pause at a couple spots here. So 500 meters long, 3.3 meters in diameter, pretty big thing, but this one doesn't go anywhere. It's point A in the desert to point B in the desert. We wanted a nice quiet place to build our thing and kind of play with the toys that are at our disposal here. Marketing likes to make these really nice videos that are just really hard for me as an engineer to walk you guys through. So that's why I like to do the slow-mo afterwards.
Was seeing just
It's really impressive and pretty,
opportunity.
but
you saw the desert completely bare, and you saw in your head, in your mind's eye, what we were going to put there. I felt really confident because
Some of my
have a
welders.
tremendous confidence.
So this is our headquarters in LA. Most of us are located in LA. We have a couple people in the Middle East working on projects. We have a handful of people in Vegas manning those sites. But of the 200 or so of us, we're primarily in LA.
And the people that I work with, and the people on the team that I helped build.
You've got teams from
It's
mechanical
our
design.
LA headquarters
teams from
again.
Computer engineering.
This is the control room. So
people
we're
who've
kind of
worked-
set up almost like an aerospace setup where we have like this mission control space where we run all the testing. So these are all engineers and kind of an expert from every field. So we have structural analysts in here making sure the tube's behaving as it should. We have somebody who's an expert on the vacuum system who's making sure that's all behaving. We have a handful of test engineers. We have one test engineer who is the guy in charge of the testing. And then before a test, we actually go through and everybody gives a go, no go before we fire the pod. So it's, you can definitely see our
Massive motor
aerospace
systems,
background
massive
there.
rocket ships and aerospace, aerodynamic engineering.
This thing that started as a sketch and an idea and then live on this.
This is the pod frame, so the CAD design, and you see that kind of shoot through here a couple
Computer
more
is now
times.
real.
This is the aerodynamic shell that goes on top. So this is kind of an idea of what the people would sit in. This is a smaller scale than what 30 people would fit inside, but
welded
gives
and
an
it's
idea.
bolted, and you can put your hands on it. And then we actually assemble all the parts onto it and set it up to site.
And then everything with these purple
flip-
lights is inside the tube during testing. So we put those lights in there so that you can get a feel for speed as we move past them. Otherwise, it was all gray tube. You couldn't really tell what was going on.
Hyperloop speed records. And to think we did all this in 10 months. We proved to the whole world that we can build safely, quickly, efficiently, and prove the technology works. This is just the beginning.
I love this one because this is Kevin, who's one of our dynamicists, being so psyched that this thing worked. One of the very first tests we did. And then I just want to pause here as these speeds come up and the dates with these. So I spent 9 months up here helping get this thing built. My job as a welding engineer was to make sure the steel tube was welded together the way it should be. These, you heard a 10-month kind of stat. That's about how long it took us from groundbreaking to first test, which is so cool and crazy. So we moved really at a very high speed for this totally new thing, and then iterated through testing really quickly, which is something we're really proud of.
I can't wait to see what we do next as a team.
Cool. So a couple more little, nope, good on the video. There we go. So just another highlight here. We hit 240 miles an hour. In 500 meters, that's pretty quick. That is full acceleration, full deceleration. We're not going to put any of you guys through that. But that was a necessary piece for us to see, really, what can this thing do? For actual passenger acceleration, we're down to fractions of G's for acceleration, less than what you'd feel taking off and landing on an airplane. But it's all programmable. We can choose all that. As far as projects we have, I've highlighted the US projects. We have an India project that's looking really good. Nothing is signed yet, but these are all kind of the progress pieces that are moving along. So the Midwest we kind of talked about. My favorite route, there's a Missouri route, there's a Colorado route, there's a Texas route, and then Washington and Pennsylvania are having independent conversations of us, which is really good for the Hyperloop as a kind of market. There's other companies that are doing this. Nobody is as far along as we are. Nobody has a test track that they've talked about yet. Some people are maybe building one. But it's really nice for the industry that the governments are talking about this without us going and asking them to. So kind of on to the Kristen side of things. Why the heck am I here? So I've had a number of people kind of inspiring me throughout my life to get me to where I am, a lot of mentors. And I unfortunately can't show everybody, so you guys get slide light now compared to what we've been doing for all the Hyperloop data. But I do want to show you a little bit of kind of my background. So as Forrest mentioned, I went to Ohio State. I originally started in mechanical engineering, wasn't great at it, and talked to a brilliant advisor who told me about welding engineering. And I switched in and my grades took off. We were a small department, so everybody knows every professor knows every student. And we really had really good relationships with everybody there. As you may have noticed, I'm a social person. I'm an engineer who likes talking to people. I'm comfortable in front of all of you here. So that's always been me. And so in school, I gave tours of the engineering department to new prospective students. And I worked in the College of Engineering. So one of the more inspirational people I've met came out of that interaction. And she was a dean in the College of Engineering and just a really cool lady. And she was probably one of the first mentors to me as a woman who really made a big difference for me, thinking, wow, women can be a big deal technically. She was really well respected by all these men. Her husband actually is a professor in the welding engineering environment, but you wouldn't know it. She didn't, follow on his footsteps or any of that. She was completely her own kind of badass lady in her own right. So she was a really good inspiration for me, kind of coming out into the world and realizing that, women in engineering can be just as technically savvy as men. And especially, I think I have it much better than she did 30 years ago or so, trying to figure out how to make it in this world. I left school and went to Honda R&D, where I had another killer mentor, and he basically taught me more about how to interact in this corporate world that I had never seen before, and how you kind of have to work your way through pieces. I worked at Westinghouse for a summer and had about the most brilliant welding engineer that I've ever interacted with at Westinghouse, and I still call him and ask his advice on things. And all these people, to me as a young engineer and to me as a student, it's so important to have somebody believe in you and have somebody tell you did good and that you're doing something right. I think maybe it's a female engineer thing. Maybe it was something of growing up in the Midwest, but I was always very unsure if what I was doing was the right thing. So to be reassured by somebody who I know is good at what they do and I know is an expert meant the world to me growing up, and it's really helped me get to where I am, and it still feels good as a person who, I'm a successful engineering manager at a cool company, and my CEO told me the other day that I did a good job at something, and it just kind of warms my heart to be able to be recognized. So some of the stuff that we've got going on here is one of my professors in engineering up on the top left. So he was my freshman engineering professor and someone that I stuck with throughout my time at Ohio State because he was heavily involved in interacting with all the students all the time. So this is actually my last day of working in the College of Engineering, my senior year. And he came in and gave us all goodie bags and thanked us for our hard work and kind of sent us off into the world. The second picture is when I was at Westinghouse, and the welders and my mentor kind of took me under their wing and said, all right, kid, you got to learn how to weld if you're going to be a decent welding engineer. So yeah, they didn't teach you enough in school. Let's throw you in here. Anybody who's done much welding, I don't know if you know, there's auto darkening welding hoods that are kind of like the new fancy thing. And when you strike your arc, the hood goes dark. But the typical way to do it is that there's always this dark shade. So as a welder, your hood is up and then you kind of knot it down. So I came in with my fancy auto darkening hood and they said, no. Give her the old broken one. You'll learn how to do this the hard way. My first weld, my mentor came out and laughed and walked out of the weld booth and came back in and said, "You weld like a drunk driver." And then he spent the next 3 months with me helping me get halfway decent. And I still wouldn't hire myself as a welder, but I can pass. The third picture is part of a student project team that I participated in at Ohio State. So we had, again, a faculty mentor who we basically were building this Frankenstein bicycle for a NASA competition. So it's called the Moon Buggy Competition. And basically the premise is that the Apollo teams in the 60s had to build a vehicle to drive on the moon. And it had to fit all these crazy requirements. Basically, they didn't want to send a vehicle, and at the last minute, someone said, all right, you can have a vehicle if you can fit it into this tiny space on the bottom of the capsule, and it has to do this, this, and this. So they set these kind of limiting rules on us, and then we take our Frankenstein bicycle moon buggy through an obstacle course. And so many bikes break. It's like things are falling apart. We're college kids who haven't built a lot yet, and we really don't know what we're doing. So it's a 3-day competition, and everybody goes through the first day and breaks their vehicle and then comes back and fixes it. And luckily we're welding engineers, so we kind of know how to weld. So we had a good shot at fixing our vehicles and came in 3rd place that year. So that was a good time. I was part of the engineering learning community. So it was pointed out to me that it's not obvious that we're spelling OHIO on the top right picture. It's very obvious to me as an Ohio State grad because we try to do this everywhere we go. And I had a peer tell me that it really looks like nothing like Ohio. But I mean, I'll just stick to we spelled Ohio. So this was the engineering learning community going to the Detroit Auto Show because the community was built to help expose us to industry and expose us to the world. So that was a cool thing we got. And then bottom right is just our little moon buggy lab in the back of the welding engineering building. So kind of ties everything into, my picture of how I got here. I came out in the world and I went to SpaceX. So psyched that they had a ton of different types of welding, and I was moving across the country and kind of by myself, and latched onto a great mentor who made me work my butt off and wouldn't tell me answers to anything, and made me look everything up in the big, thick welding codes and the handbooks and all of that stuff. But I learned so much from him. And he was kind of one of those tough guys who, when he tells you did a good job, it really means a lot. So I still talk to him on occasion. We've both left SpaceX at this point and moved on to other things. And then I came to Hyperloop and kind of get to be a mentor to other people now. So still as a young engineer and a young woman, there are plenty of people out there to mentor me, but it's really nice to be able to see the shift and be able to teach other people what all these people in my life have taught me. So I'm going to walk through one more thing of kind of what keeps me motivated now, and back to this Midwest route, because I get to kind of go back to my roots here and think about how I might be able to change my entire little ecosystem that I came from and make Columbus accessible by Hyperloop to Chicago and Pittsburgh. So I've had the opportunity to go back to Columbus and talk about the Hyperloop and meet with the regional planning commissions and meet with all these people. And I just wanted to have this slide to show you guys that, like, this is something I get to participate in, but I would never be here participating in it if it weren't for all these people who kind of led me along the way. And with that, I would love to take whatever questions you guys have. Yeah. We have not as of yet. It wasn't designed for people, and we kind of didn't start there because that technology exists. So initial testing was, let's test all these things that nobody's done before. Eventually, a person needs to go in one, and we'd like to be the first ones to do that, but we haven't yet. Yeah.
I have 2 questions.
Sure.
One is, how does this Hyperloop compares with the current existing technology, like in Japan?
Right. So the big difference is how we move the people in the pod form rather than a long train. We do go a little bit faster, which people kind of tend to over-focus on. But I think the big focus is we're moving people in kind of a packetized format rather than the large train. So on a full train in the high-speed rail or maglev systems that exist now, you still are stopping at every station. So it's more acceleration and deceleration, which uses more energy. It's out in atmosphere, so they're fighting friction more than we are and using more energy there. And then it's you as a passenger, from your experience, are stopping everywhere. So those are kind of the biggest differences. Because of all that, we can use less energy and we can build it cheaper, we think, which is, will be proven as we build our first route.
My other question is, does it have regenerative braking? Because you're spending a large amount of
Yeah.
energy to stop that.
I can't give you complete details about the regenerative braking. I figured we would get a couple questions in before there was a question that I couldn't tell you the answer to. We have lots of proprietary things, and for all I know, you all work for the other companies. So I can't give you all the answers. But that's a really good idea, and I will leave it at that. Yes?
How much is the estimated peak power consumption?
Ooh. That's actually a question I don't know the answer to. Good question. All of our calculations have been to make this a better option for a government or somebody putting in a train than high-speed rail and maglev. So I know we're below. Maglev is typically the one we compare to. I know we're below those guys, but I'm not sure what a number is. Sorry about that. Yeah, in the back. Yeah, the full history is Elon Musk in 2013 wrote a white paper and basically said, hey world, there's this thing. It's called a Hyperloop. Here's how it generally works. Someone should build it. So our company started up, another company in LA started up, a company in Canada called Transpod started up, maybe a year behind, and Elon Musk picked up a student pod competition. So at SpaceX, they actually have a mile-long, 1-meter diameter tube where they pull vacuum and they propel pods through there. There's not a propulsion system in that system. So they're kind of two of the three systems. The cars get pushed with basically a little Tesla that shoves the student pods along. So they've done that competition 3 years in a row. And actually a number of companies have spun off from those student teams. So now there's more companies than ever around the world working on Hyperloops. Yep.
I assume it would be competing against airlines then, right?
Yes, with an asterisk. The long haul flights like in LA to New York, it never will make sense for us to build so much infrastructure in one go. Maybe we connect a bunch of smaller routes. So with those longer flights, no. More like the 1 hour, hour and a half, 2 hour flights. We talk a lot in LA about the LA to Vegas flight. And there's a flight every hour from LA to Vegas. And it's a 45-minute flight, but you get on your plane an hour or half an hour early. You're at the airport how much before that? So altogether, it's a 2.5 hour thing, and it's 22 minutes on a Hyperloop. So those are the flights that we're probably competing with. We've spoken with a couple of different airline experts, and they've told us that those are actually the flights that the airlines make the least money on, but they need them because you need the accessibility for everybody. So it'll be interesting to see how that ties in those regions, with maybe airlines are able to drop those lines, or maybe we start a battle with them. We'll see. Yeah. Yeah, it's all, do you mean construction costs or ticket prices? Yeah, so it needs to be affordable enough to be able to take it every day. I think it's between the cost of like a metro and a flight, but we did a feasibility study on the Missouri route connecting St. Louis and Kansas City in Missouri, and the ticket price was less than the cost of the tank of gas to go from place to place, which is pretty cool. Yeah.
Can we estimate the mass of the vehicle about 2 times the car, normal car?
It's more than that because of, let's see, how much of this can I tell you? In iterations from our DevLoop testing to the production vehicle, we have tried as much as possible to move all of the kind of smart stuff from the track side to the pod side, so that basically the design is as future-proofed as we can get it. And as we need to upgrade things, we don't shut down the entire route to upgrade the track. We can pull out a pod and upgrade the pod. So because of that, there's a lot of weight on the pod. And it's significantly more than a vehicle. And that's kind of one of our constant goals is as we iterate on our design is bringing down pod weight.
So lots of momentum.
Yes.
Lots of momentum.
Yes.
Any shake now, areas that you mentioned, any ground shake?
Oh, definitely. Yeah.
That's a big concern.
Yeah, even in Las Vegas, where our test track is built, it's an active earthquake zone. So everything is built to all the civil engineering earthquake codes. And then what we're doing right now, our design has been kind of mature for a while, and mature enough where we can go in and basically try to break it. So we're spending a lot of time, we know our design better than anyone else. So we're spending a lot of time as we design things, going in and if I'm a designer, for example, I'll go in and review my own design and see what are the ways that it can fail, adjust the design, fix those ways, or come up with mitigations and tests that might prevent those. And then I'll give it to you and you'll go through and try to break it. And so this is a lot of what we've been doing in the last year or so in preparation for basically presenting a package to certifiers or regulators and saying, here's why we think this is a safe system that people should travel on. And what do you think? And then there's some expectation of a back and forth there. And at some point, a track comes out and people will go on it. But safety is huge. You guys have less questions than I expected. Yes.
Elon Musk, you just mentioned, is working now on the boring company.
Yeah.
And underground. So I'm wondering
Yep.
about if they're developing underground transportation tunnels.
Yeah.
You know, why did you've chosen above ground?
Mm-hmm.
Is there a potential to go either way?
Definitely. And most of our routes have both. Above ground in the vast majority of locations is cheaper right now. If Elon can make some crazy leaps with tunnel boring, then awesome, because underground is way easier to interact with kind of the world around you. So right now, most of our routes tunnel into the cities because you guys have a same traffic issue as LA. If I put the station on the outside of the city, why are you going to the station? Just go to the airport. It's easier. Or take the way that you're used to. So we need to be in a city center, which means that we're tunneling in to get to the portal. There's often geographical features. So on our India route, there's a good amount of tunneling. But in general, staying above ground is cheaper. So that's the main goal with that. Yep. Yeah.
What's the projected frequency of the pods moving through the line?
Yeah, good question. Multiple pods per minute. So they are spaced apart for stopping distance for safety. But from a technical standpoint, they can be, feet apart, which is pretty cool. And there's some aerodynamic advantages to keeping them tighter together. So we're in a vacuum, but there's enough air that still we have aerodynamic effects. So we've spent a lot of time kind of perfecting those aerodynamic effects and looking at really convoying pods is what we call it. So thinking of how you may convoy semi-trucks. And the first vehicle takes a lot of the aerodynamic load, and then the vehicles behind it get some aerodynamic advantage to a certain distance. So we've been optimizing that and really working on, so maybe those pods aren't all going to the same place, which is why they're individual pods with different people on them. But from LA to San Francisco, we have a convoy of 5 pods, and then one of those pods peels off, and then we have 4 that go to the next spot. Maybe another pod hops on. So it's kind of a cool trick that we can play with our already pretty efficient system. And that's new news that has just become public recently. So this is the first group I've been able to tell about that. Yes. No, and we spend a lot of time evaluating that. So what happens if the tube becomes punctured? And stepping back, our nominal operation, if anything goes wrong, is stop all the pods, evaluate the situation, and in a lot of cases, we bring air back into the tube. If for no other reason than to just make sure that if people need to evacuate the pod, they can. So say there's a fire on a pod. There's steps to take to put out the fire, but then also air is coming back into the tube. So looking at how often valves are placed to bring air back in. What does that valve do to a pod traveling past it at 1,000 kilometers an hour has been a big focus of ours. And for DevLoop, our test route, there was a big focus on this because if we had some issue happen and we buckled the tube, we're done. So we spent a lot of time evaluating that and haven't had any issues with our pressures and with the particular geometries of our pod. There's somebody back at that. Yes. Yeah, we do. We're about like flying at 200,000 feet. So we're 100 pascals. Vacuum is, depending on who works in what region of vacuum, the units are all kind of fun for people to relate to. But it's like high atmosphere flight. We played around with whether we use airlocks or air docks to bring people in and out of pods, and have made a decision that I don't think is public for me to talk about yet, but we basically did engineering evaluation on both options and have chosen one going forward that we think will work really well for people. Sorry, it's a non-answer. It's somebody...
Can you tell us
Yeah.
about your role with the welding? What
Yeah.
kind of welding did you do, and what are the requirements of welding a vacuum vessel?
Yeah, it sounds like it should be really hard, right? Like this thing has to hold vacuum. It's 500 meters long. DevLoop is like the 4th largest vacuum in the world, vacuum chamber, which is ridiculous because most of those vacuum chambers are like particle accelerators or really fancy, clean, high vacuum things. Ours is kind of filthy. And at our vacuum levels, it's okay that it's that way. It's a little leaky, but none of the welds leak because they're 4 or 5 pass welds. So my CEO had complimented me on no leaky welds after our first pump down. And I said, well, if the welds are leaking, you should probably fire me because that means there's a crack through 6 passes of welds that our inspections missed somehow. So it was pretty standard structural welding requirements, actually, which is pretty cool. It's all basic steel. So we hired pipe welders to come in and put the whole thing together, and they did a great job. We're getting into weirder welding as we go. So the motor segments, for example, have copper coils connected to copper bus bars carrying all this current. Those were laser welded at our headquarters. We have a lot of kind of electrical applications where we're welding fuses or wires. And these are things that need to last a long time and maybe have some mechanical cycling happening, but maybe also have electrical cycling and thermal cycling. And then, oh, by the way, everything's in a vacuum. So everything that gets warm stays warm because there's no air to pull the heat away. So there's some weird aspects on the welding side of how things behave once they're welded. My role now is covering the welding and all of the materials side of things. So our team helps all the designers and the manufacturing engineers choose materials for every system and then make sure they're going to last as long as we would like them to. So that's where, for our non-metals engineer, she spends a lot of time worrying about how heat affects her polymers and how they break down and how we can test something in a shorter amount of time to say it's going to last 30, 50, 100 years. So it's an exciting thing to be working on. Yes?
Regarding electrical energy consumption,
Mm-hmm.
so you have solar panel on the top of
Yeah.
Does the energy generated by solar panels enough to drive the loop for 24 hours?
Yeah, it's probably not always, especially at peak times. And I think it will be a supplement. Perhaps at off-peak times, it's more than enough. And maybe we can feed some energy back in. So this is where we kind of think of how, and of course, every region is different. If I'm building something here versus LA, I'm probably not going to get as many sunny days up here. Although everybody keeps telling us it's going to be sunny tomorrow, so we'll see. So different regions have different availability of energy. So we evaluate all of them separately. But we have a big hope that as part of a grid, our system can be kind of this bank that will help feed energy or pull energy more logically, especially in a place like India, where the grid has a lot of issues and there's a lot of blackouts and brownouts happening throughout time. So if we have this kind of big thing that takes a lot of energy but maybe has the ability to store energy and feed it back, then it opens up some possibilities for what we can bring to the region other than fast transportation. Yes?
Is thermal expansion of the tube an issue?
Yes, definitely. Especially, well, concrete expands too, but the steel is definitely a fun one. So we had a couple of different designs for how to handle thermal expansion on our DevLoop system and ended up coming up with one where each tube sits on a saddle. And actually, let me go back to a good picture. Maybe this is a good one. Nope, you can't see it there. No, you can see it on this one. So you can kind of see really tiny little saddles that interact between the tube and the column. So the saddle is rigidly connected to the tube, but it is not rigidly connected to every column. And there's a very simple sliding joint, because this thing's designed to last 5 years, 10 years maybe. There's a simple sliding joint where a nicely polished piece of steel on the bottom of the saddle slides in a nicely polished channel on the column. So the whole thing can grow and shrink. This is 500 meters long, and between the hottest Vegas summer day and the coldest Vegas winter night, it changes length by 0.5 meter. It's fun because sometimes the hottest Vegas summer day and the coldest Vegas summer night are pretty close to that same range of time. So we've got a lot of movement happening, subtle at each column, but over the entire length, a lot of movement. So we went pretty simple here because this is a short distance. On the production systems, there's a much more kind of mature thermal expansion design. But yeah, everything has to be designed for thermal expansion, from the tube to the track elements. Everything inside the tube, as I had mentioned, gets warm and stays warm, or gets hot and stays hot. So thinking about how materials interact with one another is another big piece of what my team is working on. That's it. Yes?
Just a few questions regarding safety.
Sure.
A few in one. In the event that one pod lost the ability to receive power, and a bunch of pods together,
First, communication. So there's redundant systems that talk to that pod. So we know that it's got a problem. If everything's going at speed, then that pod's not going to immediately break. And we're designing our system such that if a pod loses, basically failing happens in a gradual, safe way rather than a sudden, oh my, let's stop way, because you're going way too fast for that to be a survivable incident. So if a pod loses power, it will start to coast. The other pods around it will quickly figure out what's happening and start to coast. So the spacing between the pods, even in a convoy, takes all this into consideration. And then everything eventually slows down, stops. We remove broken pod from the system, and then check everything and set up and go again.
one more question.
Sure.
I don't know if this term is correct, but what if pressurization is lost in the pod?
Yeah.
What happens to the people, and how do they escape? If there's any general emergency like a fire, actually get out of the pod and get down from the hyper.
Yeah, good question. And you can look here and see, okay, we're 22 feet in the air at the end here. So you're stuck in a vacuum tube and then you're up in the air. So yeah, right, not great. The nice thing is so the pods are all at normal atmospheric pressure, so not a reduced pressure like you feel in a plane, which gives us kind of a greater distance before we get to danger zone on enough air to breathe. So there's a warning for that. Let's say there's a fire and that's accelerated things. We're working on how we detect a little fire, because if there's not, a flight attendant basically to say, oh, somebody's got a fire in their lap, we need to make sure that the system can figure out that a little fire is happening, because that's still affecting the amount of oxygen in the pod. But basically, a lot of sensors are keeping track of everything. And the nominal emergency procedure is bring everybody to a stop and bring air back into the tube, which means we move slower, but then those pods move to an emergency exit point. And so those are spaced every so often along the route. And basically there's kind of this emergency portal for where to take people. And as we are taking the pods there, emergency personnel is being directed, because sometimes these locations are out in the middle of nowhere. In India, there's lots of open space between the cities. So getting emergency personnel to that spot is important. So organizing and making sure that they're close enough that in the time we have an issue, we can get them there is good. But it's nice because a plane has an issue and they need to land. We have an issue and we can repressurize the tube much more quickly than a plane can land and basically give people oxygen again. So there's still, a couple minutes of kind of harrowing time of, people are panicking probably and trying to figure out what to do. But we have really a lot more time or a lot shorter time to get to a safe situation than, for example, a plane would have in a similar situation.
Okay, I'm sure that Kristen will take some other questions after the talk. People want to leave. Please feel free to come up and chat with her. But if you would all join me now in thanking Kristen for the